In this video, I would like to show the design of 8-bit full adder using IP integrator. Verification of the design is performed using virtual input output and integrated logic analyzer. I have already created a new project with product family, that is RTX 7 FPGA, and the part name is XC7 EA35 256 with speed of -1. So let's start the design of 8-bit full adder using IP integrator. First, click on create block design. Click OK, or you can change the design name. Click OK. It opens a new view, a diagrammatic view. Here you can create the block level designs. Add the IP cores by clicking on this add IP, or you can click right click here and add IP. Both are same. Search for adder. Double click on it. This is the basic module of a adder. Double click this module. You can change this. Change the mode to unsigned or signed based on the application. Press here to enable this pin. Change it to unsigned. Change the input width of the first operand to 8 and second with the 8-bit. The add mode is either I could choose an add, subtract, or add subtract. Right now I am using add, and the output width is 8-bit. You can have the control signals. Right now I want to disable this clock enable, and I want to have carry in, which is of 1 bit. A and B are the two other operands. I want to have a 8-bit sum and single bit cout. You have a lot of pins which are disabled here. I want only these pins. Clock is the default. Click OK. Now I want to verify this particular design or adder or subtractor by using the virtual input output and integrated logic analyzer. Right click to add the VO module. Search for VO, virtual input output block. The output has to be input to this block. So there are three inputs right now. A is 1, B is second one, and clock in, which is a 1 bit. So I'll set the output of the VO. Double click on it. Here the output probe will have 3, and the input will be the outputs of the adder block. So I am providing it with the 2. Now I have the inputs. Both the inputs are, one is 8-bit, the second one is 1 bit. So let me give this as 8-bit, and the second one is 1 bit. Similarly, the output probe, A and B are 8 bits. So change this to 8 and this one to 8 and carry or the Cin is a 1 bit data. Click OK. Connect the blocks. 8-bit data, and this is a single bit which is a Cin. Now connect the output 8-bit data to this probe of 8-bit. Zoom it so that it is visible to you, and the 1-bit data is connected to this. Clock is a common signal, and you can make this as external, or select the pin and make it as external. Let me delete this first. Make this block as external because it is a common clock here. Now you connect the clock to it. Now the designing is completed. Now I want to integrate it with, or this VO will provide the input and output to this. That means this is acting as a input output block. And now I want to add one more IP, which we call it as ILA, integrated logic analyzer. ILA is similar to that of your CRO or probe scope. Provide the number of inputs and outputs. If you observe this, these two are the outputs and these three are the inputs. So totally 5 signal has to be mentioned here. Mention it as 5. Check the output ports. Select the output ports. I have input width, that is probe A is of 8-bit width, B is also of 8-bit, and Cin is of 1 bit, and sum is of 8-bit. Click OK on this. You can directly connect the common clock. Now you provide the connections. This is A, which is a 8-bit data. Next B, which is a 8-bit data. Then we have the Cin 1-bit data. Then we have the 8-bit data from the sum. This is the sum line. Connect the carry out, which is a 1 bit. The design is complete. So to check the design, you can click on validate this design if there are any errors for it. Validation is successful, there are no errors. Then click on regenerate layout. So this is the view of the design, which is a 8-bit adder. Once the design is completed, go to the sources. Here we have the design in blocks. BD stands for block design. I want to generate a Verilog out of it. Click on or right click, create HDL wrapper. It will generate the number of inputs. We don't have any outputs because we are observing on the integrated logic analyzer. It has generated the Verilog module or Verilog file for this entire structure. Just double click on it or to see the designs. Now it has only one clock as an input, because in the block design also we have only one. By providing the clock, generate the outputs. These output will act as input to the other blocks. That is the adder. Once the wrapping is done, directly you can go to the run synthesis. Click OK. Observe that the synthesis process started. It takes time to complete this process. Let me pause the video for some time and I will return back. Once the synthesis is completed, click on Open Synthesize Design. Click OK. It shows the IO planner. It shows the IO planner of the FPGA board. This is the board which I am going to use. RTX 7 FPGA development board, and in this is the clock signal which is used for this simulation. It has a pin as N11. So I am going to use that pin package. You can click here, then see the scalar ports. In that we have the clock signal. The clock signal is not assigned with the package pin. Click here and search for N11, which is a clock generator, and change the IO standard to LVCMOS 33. Once the assignment of package pin and IO standard is done, save the design by pressing Ctrl S. Click OK. Provide the file name. Let me call it as pins full adder. Click OK. This is the constraint file which we have done. We have assigned the constraint file. Then once the synthesis is done, click on run implementation. If you want, you can view this. Here it is located. This is the pin which we have done. N11 fixed, which is a clock. Click on run implementation. Click OK. Implementation part also is a time taking. I'll pause this video for some time and return back. Once implementation is successful, click on Open Implemented Design. Click Yes. This is the implemented design of a 8-bit full adder. Here you can observe the power, reports, DRC, methodology, and timing analysis. The next step is to generate the bit stream. Click on Generate bit stream to load it into the FPGA. Click OK. So it has started writing the bit stream. The main aim of this design is, see that we haven't written any programming. We did the block level design of this. There is no test bench program here. We have used only the blocks by using the IP catalog. This. create the block design. Once the generation is done, you need to just program the device. Here it is a 8-bit adder. That's why it is taking a bit time. Now once the bit generation is completed successfully, click on Open Hardware Manager. Right now I don't have any hardware here. It is no hardware target is open. At this moment you need to connect the FPGA board. I have connected the FPGA board to my laptop. Once it is connected, click on Open Target, then Auto Connect. Now it detects the board. This is the package, and this is a Xilinx. Now it shows that it is connected, but it is not programmed. So click on this program device, then it takes two files to program. Click on Program. Now the device is programmed successfully and it opens two windows which we call them as hardware virtual input output VO and hardware integrated logic analyzer to view the waveform. So first go to the VO and click on add probes. These are the signals which you need to add. Click OK, and if you want you can change this. So these three are the inputs: 8-bit data, then it is a 1 bit, and I have the output which is sum 8-bit and cout carry with 1 bit. You can change this. Instead of hexa, you can change the mode by right click, then change it to binary. Here also the same process, right click, change it to binary. It is already in binary. Change this mode from hexa to LED also. The low value will be red and high value will be blue. Here also you can change the red as low and high value to green or blue depending on the choice. Now the initial values are all zeros, so result will be a 0. 0 means it is a low value. Now you can see this in the ILA. Click on run trigger. Now the value is all zeros. Change the input here, maximize this. Change the input in VO. I'll assign the value 8-bit data as 111. Now see the result. Now it is in a sum is in a hexa. Let me replace it with the binary. The sum is 1 because we are adding the two 8-bit data 000 and 111, and the result is a 111. Check here. You can see that you can directly change the values to binary. These are the result. Similarly, you can have all the values, change the all values to 1 1. Here also the result has changed, and this value to 1 1. Randomly I am giving the value, and carry in will be changed to 1. So lot of changes I have done. You can see this effect in the ELA. Click on here, see the values. In this way you can verify any bit length, 8 bit, 16 bit, or 32 bit, 64 bit to 56. Like that you can increase the bit size and verify the design by using the VO and ELA.